Good morning, everybody. Thank you for joining us on this webinar. So the topic of today's presentations are as follows. First, I will talk about the cause and effects of electric motor noise. Then I will discuss about electric motor noise simulation. I will then give a short demonstration of electric motor noise modeling. And then I will present the conclusion, and we can then go to the question and answer session. Why should we care about electric motor noise? Well, electric motor noise are used in many different products that we use in our everyday life. For example, we brush our teeth at least twice a day, and some of you are using electric toothbrushes powered by electric motors. We also clean our homes with vacuum cleaners, also powered by electric motors. Both the electric toothbrush and vacuum cleaner make noise, and they're not the pleasant kind of noise, of course. The noise produced by electric motors can be a disturbance to the people who are nearby. And not only that, the electric motor can be perceived as an indication of quality issue. For example, let's look at the electric motor noise in electric vehicle. With the absence of the internal combustion engine and additionally the reduction in numbers of noise sources in electric vehicles, the noise behavior that were previously acceptable can now be clearly audible and perceived as an annoyance. Electric motors generally produce higher frequency noise. For example, the whine noise. Whine noise is tonally measured and typically is in the range of 400 Hz to 2000 Hz, and it can be annoying to the people riding the car. The electric motor noise in an electric vehicle can radiate noise directly from its housing, and this is called airborne noise, or through the structural mounts of the vehicle, and this is called structure-borne noise. So what is causing the electric motor noise? Each motor produces desirable forces, torques, and motions in addition to those that are undesirable. Such undesirable forces and motions cause vibration of the motor parts that we hear as noise. So the noise and vibration produced by electric motors can be divided into different categories based on the noise generation mechanism. One cause of the noise is the electromagnetic forces. The magnetic energy that is needed to generate the machine's torque in the air gap between the rotor and the stator must fluctuate in time and space. This fluctuation is influenced by a lot of factors, such as the design of permanent magnets and the distribution of the winding. These fluctuations cause radial forces that deform and create movement of the stator and rotor structure. So what I'm showing you right here, this is an animation of the stator deformation due to a simplified radial force. Another source of noise is caused mechanically, such as from contacts between the shaft and the bearings, and from imbalances due to the manufacturing tolerances. Yet another noise source category is associated with the flow of air through the motor. This type of noise is related to the turbulences that are generated by the airflow. Now let's focus on the noise due to the electromagnetic forces. The primary noise radiator in an electric motor noise is the stator frame. So if the frequency of the radial force on the stator teeth, as shown right here on the right hand side, is close to or equal to any of the natural frequency of the stator frame, resonance will occur, and that leads to the deformation of the stator, which in turn causes vibration, which we ultimately hear as noise. The cause is the radial electromagnetic forces generated in the air gap between the rotor and the stator. So if you see here in this illustration, the radial force is applied on the stator teeth right here. The purpose of the forces generated in the air gap is to have only the tangential force to cause the desired movement, which is the rotation of the rotor. However, it is unavoidable to have radial force components that comes along with the tangential forces. The result of this radial force is an excessive radial deflection of the steady shape of the stator frame structure. In other words, the radial force right here causes the deformation of the stator structure. Now, this is a simplified animation of a couple of vibrational modes of around a stator frame structure. When the normal shape of the stator frame is deformed, and this is dictated by the unbalanced radial force vector in the air gap, this causes vibration, which we will hear as noise. What does an electric motor noise look like? Here we can see an example of the noise spectrum from a stator that is attached to a housing. We can see some peaks here, and in this example we have a major peak around 2600 Hertz. The peaks that we see here can be correlated to the structural displacement of the stator housing system. Therefore, it is usually important to analyze and compare both the structural results and the acoustics results, as acoustics is the product of structural vibrations. So, by looking at both the structural results and the acoustics results, we can determine the cost of the noise, and ultimately we can find the solution to the noise problem. How can we mitigate the noise problem? Well, in general, there are two main strategies to reduce noise. We can either reduce the noise at the source or reduce the noise by changing the transmission path. Let's look at the first strategy, which is to reduce the noise by controlling the source. To reduce the noise at the source, we can make changes to the vibrating structure, for example, by making the structure more stiff. Adding stiffness to the structure will change its natural frequency. This way, we can detune the structural response from the force input such that we will not excite the resonance frequencies. Another way to control the noise is to put an enclosure around the noise source, such as this one, or we can put a dampening material, such as this acoustics foam, to absorb the noise. The second strategy of noise reduction is through the modification of the transmission path. There are two noise transmission mechanisms. Noise can be transmitted through airborne path or structure-borne path. Airborne noise is vibration transmitted in the form of sound waves through the air. To reduce airborne noise, we can put the source, in this case the electric motor, in an enclosure, or we can add dampening material like I've shown you before, such as porous material, or in this case this acoustic foam here, to absorb the acoustics energy and hence reduce the noise. Now, a structure-borne noise is vibration transmitted through structures, and we can mitigate this type of noise by changing the structural properties of the motor and the surrounding structure. For example, we can put a stiffener to make the structure more rigid, or we can try to decouple the motor with the rest of the structure by using mounts, such as the one shown here. Now, let's talk about electric motor noise simulation. With the noise that electric motors produce, how can we design a quieter product? Well, the answer is simulation. We all need short development cycles to improve competitiveness and also reduce the overall development costs. We also need robust solutions that will work for various situations, and that means that we need to test several different designs and do several different simulations. And this leads us to acoustic simulation, in this case specifically the electric motor noise simulation. Therefore, I would like to talk to you about electric motor noise simulation with Actran software. What is Actran? In a nutshell, Actran is a general-purpose finite element software for modeling sound propagation, transmission, and absorption in an acoustics, vibro-acoustics, or aeroacoustics context. So to analyze electric motor noise, we want to model the acoustics radiation from the motor. And there are two ways to do this electric motor noise radiation in Actran. We can do a fully coupled computation or a weakly coupled computation. A fully coupled computation is where both the fluid and the structure are modeled within Actran and they're solved together. A weakly coupled computation, on the other hand, is where Actran model is limited to the acoustic part only. The vibration of the structure is computed with other structural analysis code, or it can be experimentally measured. The displacement field of the structure is applied to the acoustic mesh by a boundary condition in Actran. Now, let's look at the fully coupled computation more closely. In a fully coupled computation, Actran computes the structural vibration as well as the acoustic radiation. So to analyze electric motor noise, first the electromagnetic forces are calculated by an external software such as JMag or Magnet. And these electromagnetic forces are then used as the excitation to the structure and also the acoustic radiation model. Actran computes the structural vibration of the noise and the radiation and gives related quantities such as pressure at the microphones and the acoustic radiated power. We can also view the directivity pattern of an electric motor, like this one for example, or we can also view acoustic pressure distribution around electric motor, such as this one, for example. In a weakly coupled computation, Actran computes only the acoustic radiation. The structural vibrations are computed by other finite element codes, such as MSC Actran or Actran itself. The process is similar to the fully coupled computation, but here the structural simulation is done separately from the acoustic simulation. So in this example, the electromagnetic simulation could be performed in JMag or Magnet, and the structural simulation right here could be performed either in Nastran or Actran. The results of the simulations are then fed into Actran to compute the radiated noise. We can still get the relevant results such as acoustic pressure and radiated power, and we can also still view the directivity pattern of the electric motor and the acoustic pressure distribution around the electric motor. I would like to mention a couple of case studies from our collaboration with other companies. The first case study is the one we did with Renault on electric vehicle noise simulation. We mentioned earlier that the challenge in electric vehicle is the absence of internal combustion engine. It exposes other noise sources that were previously acceptable. For example, the motor noise. The end user of the electric vehicle, of course, expect the electric vehicle to be very quiet. And during the development of a new electric powertrain, Renault has to determine the NVH requirement of the new motors before the physical prototyping itself. Our solution was to read the electromagnetic forces calculated by Maxwell 2D into Nastran. Then Nastran performed the vibration analysis. The vibrational levels computed by Nastran were used as an input to Actran to predict the noise radiation. Now this one is another case study where we did a weakly coupled simulation of electric motor noise in Actran. The electromagnetic forces were calculated by Magnet, an Infolytica software, and then it fed into Actran via FSI mapper to simulate the structural vibrations. Actran then takes Nastran vibrations results to simulate the noise radiation. To show you how electric motor noise simulation could be done in Actran, I would like to show a short demonstration of an electric motor noise modeling in Actran. In this demonstration, we used the 2004 Prius motor, as shown here, as the base of our model, and we only modeled the stator and its housing or the frame. The geometries are simplified, but we followed the original dimension fairly closely. So the original dimension you can see here. We excite the stator teeth here with a sine function to simulate a simplified radial forces acting on the stator teeth. Once the structural vibration of the stator and the housing has been computed, we then use that as the input of our acoustic model. The acoustic model will propagate the acoustic wave from the surface of the stator housing into a free field, or an open space, if you will. Now, the first step in the modeling process is to perform structural simulation of the stator and its housing. From the structural model, we can compute and analyze things such as the normal modes of the stator and the housing together, and we can also look at structural displacement, etc. So normally, the electromagnetic forces are computed by other software such as JMag and Magnet. However, for this simple demo, we are using a simplified analytical solution of the radial forces to load the structural model here. So in this first step right here, we use Actran vibro-acoustics capability. Now let's look at the structural model. The blue part that you see right here, this is the stator, and the green part here is the housing. Both the stator and the housing, they are modeled as solid. And the two parts are connected with beam and rigid body element. Let me show here. You see this red elements right here. So the beams and the rigid body elements, they represent the bolt that connects the stator to the housing. See, okay. So from this model, we can do the structural analysis, and now let's look at the normal modes results of this model. What I'm showing you right here are the animations of the normal modes of the stator and the housing. Keep in mind that the stator and the housings, they're connected. So this is the first 6th, 8th, and 10th natural modes of vibration of the stator and its housing. And on the left-hand side, you can see the first 10 natural modes of the stator and the housing. We loaded the stator teeth with a simplified radial force. The simplified radial force is a sinusoidal function as shown in this plot on the left-hand side. And the amplitude of the sine wave or sine function depends on the relative location of the stator teeth. In other words, the magnitude depends on the relative angle of the stator teeth as shown in this picture right here. This plot here, it's showing the x displacement at several accelerometer locations marked by these red dots right here. We can see some peaks which are related to the normal modes of vibrations. For example, the first peak right here is due to the 4th vibration mode, and the second peak here is due to the 9th mode of vibrations. You can also plot the color maps to show the displacement at certain frequencies. For example, I'm showing here the color map of the structural displacement at 1.1 kilohertz and 1.6 kilohertz. These frequencies are close to some of the natural modes of vibrations. We can also look at global indicators such as the mean square velocity of the stator and the housing surfaces. The blue line right here, this is the mean square velocity of the stator, and the red line right here is the mean square velocity of the housing. The mean square velocity is one indicator of how efficient the noise radiation from a surface is. As we see here in this plot, the structures do not radiate equally at all frequencies, but instead there are some frequencies where the noise radiation is more efficient than other frequencies, as evident by the peak at 2600 Hertz here. Now, the second step in the modeling process is to perform the acoustic simulation. In step 1, we compute the structural vibration. So in step 2, we use the structural vibration as the acoustic excitation and compute the radiated noise from the stator and its housing. The end results are acoustic quantities such as acoustic pressure at the microphones and acoustic radiated power. Now let's look at the acoustic model. So this is the acoustic model. The acoustic model consists of a coupling surface where we take the structural vibrations and apply it as the acoustic excitation or acoustic sources. So the coupling surface in this case is this red mesh right here. It's like a wrap around the stator and the housing. We call it shrink wrap actually. Now the gray area that you see right here surrounding the coupling surface, this gray area represents the air around the structure. Outside of the gray area right here, just right outside of the gray area, there's a skin, if you will, to represent a non-reflecting boundary condition so that we can model an unbounded space or free field propagation. This non-reflecting boundary condition will allow us to get acoustic pressure at virtual microphones located outside of the computational mesh. So in this model, I have 3 virtual microphones located outside of the computational mesh. So if you can see, there are 3 white dots, one right here, and one right there. I can get the acoustic quantities on these virtual microphones even though they are outside of the computational mesh. Even these 2 microphones, they're still outside of the computational mesh. So that's the benefit of having the non-reflecting boundary condition here. So this is an example of sound pressure level at those 3 different microphones that I've shown in the model. And the microphone is on the top, right, and left-hand side. This plot here is generated by the built-in post-processing tool in Actran, and it's called the PLT Viewer. PLT Viewer makes it very easy to post-process the acoustic results. Now, let's look at this curve here. We can observe a maximum peak at around 2.6 kilohertz. This is actually related to the structural results that we discussed in the previous slides that I'm showing right now. So as we can observe from the plot of the structural results right here, in this case the mean square velocity, and if we look at the sound pressure level, we can see a peak at the maximum peak at 2600 Hertz. This is to show that the peak we observe on the sound pressure level plot is related to the peak that we observe on the structural results. You can also plot the acoustic pressure around the housing. For example, we can see the acoustic pressure around the housing at 1.6 kilohertz, where you see a peak right here, and also at the maximum peak at 2.6 kilohertz. Using both color maps and plot, we can visualize the sound field at these 2 peaks frequencies. Another way to view the results is by plotting the structural displacement alongside the sound pressure field. So in this illustration, I'm showing the housing displacement on the left-hand side and the pressure field on the right-hand side at the maximum peak of 2.6 kilohertz. When we look closely at the mean square velocity values and the sound pressure levels, we can see that there is a correlation between the structural vibrations and the sound pressure level. The peak at 2.6 kilohertz here that we saw in the sound pressure level is due to the stator vibration. Now, let us conclude the presentation by summarizing what we have talked about. So in conclusion, noise can play an important role in electric motor design, as it can be perceived as either a quality issue or simply just as annoyance. Acoustic simulation helps to design quieter electric motor. Simulation can shorten the development cycle and also reduce the overall development cost. And we have demonstrated how Actran, the leading acoustic software, can perfectly model electric motor noise. With that, I thank you for your time, and I open the question and answer session. If you have any question, you can email support.na@fft.be.